and we have Spark. You know about it. It's a great framework. It's unified. It's open source parallel data processing framework for big data analytics. And you remember that we talked that we have very nice options. Its ability to do batch processing. We can do real-time processing. We have stream analytics if we need it. We have machine learning, and we have interactive SQL. And today we will talk about machine learning, part of Apache Spark. And you see here these modules. We have Spark Core Engine, which can be executed on a Yarn scheduler, Mesos. It could be standalone scheduler, and it also could be Kubernetes. We tried previous our class standalone scheduler, and also I show for you Yarn, how it looks like Yarn scheduler. And on the next class we will talk about Kubernetes scheduler. So I want you to see the whole picture of our learning, and you see what parts of this system we will learn and what we will do. So we have Spark ML. It will be today our topic, and also in the next hour class we will talk about Spark streaming. Previously I have shown you a few tools for streaming, but in the next class we will combine them together. So today we will talk about Spark ML, what is it and what part of it we have. In the first hour classes I also explained for you what is ML. It's machine learning. It's a part of artificial intelligence. Yes, we have artificial intelligence combine two large domains. It's machine learning and it's also deep learning. Deep learning, it's about neural networks with multiple layers, and if you're talking about machine learning, we are talking about statistics, linear algebra, optimization, probabilities, statistics, and that's all about machine learning. And I also talk and explain for you main ideas what we are talking about in machine learning, and we will talk about these terms, about main concepts in today our class. So let's move forward. If you're talking about data processing in the Spark, we have some workflow, and this workflow could be described or depicted as in this figure. And you see that we have data ingestion, we have data cleaning and transformation, we have model training, testing and validation, and deployment. This step could be done multiple times, because when we train our model, we test, validate it, and train it again. If we don't meet our requirements, if you don't meet needed accuracy, we should train our model more and more times, and maybe configure hyperparameters of our model. That's why we see this arrow here. Also, if you look precisely in this workflow, we can see additional details. What are these details? It's at first ingestion. We could do ingestion from CSV files, from HDFS. It's also about format. We are talking about Parquet, about Avro, about JSON. A JSON format commonly used in internet in a REST application. Avro format can be used when we are doing stream processing, when some data comes to our cluster or our computational system from some streaming application like Kafka or another application, and usually we can use Avro format, and this Avro format also support schema. And if you are using Kafka, we also use additional tool which called Kafka registry, which allows us to share schema of data we are transferring in data streams. Parquet format commonly used as very effective, compact and distributed format for batch processing. And we also see here that we have displayed schemas, we have real-time and batch processing. Yes, we have we can provide data integrity and security. This all we can provide by choosing proper format, and also we can add here not only CSV, HDFS, Parquet, Avro, JSON. We can also add here as a source of source information could be also relational database management system, RDBMS. It could be Postgres or Oracle or another database. And what we are talking about when we are talking about data processing, we are talking about pipelines in ML toolkits, and these pipelines could be built with tools like scikit-learn. Scikit-learn is the most famous and functional toolkit written in a Python and using by data scientists, and also R. It's package for statistical data processing, for statistics, for analytics. If you're talking about Spark ML Leap, it's also about some techniques which are used in scikit-learn, but I can say that this Spark ML Leap we will talk about is less functional than scikit-learn, but scikit-learn allows you to run your tasks in a parallel only in a SMP systems, in a symmetric multiprocessing, but Spark allows you to do it in a cluster. And TensorFlow transform, this is TensorFlow toolkit, well known also, which was created by and supported by Google. You can look on it also. This package is also designed for deep learning and neural networks. Also here could be added package PyTorch, but I didn't. It's not my slide. I was borrowed this slide from IBM. I found it in internet, and I think it's rather interesting and rather informative for you. Also, we have in the stage of data processing ability, or sometimes we are doing data visualization. We are doing feature transformation and engineering. We are doing pipeline. We are creating some pipelines of transformers and models. So at this stage we extract these features, we transform these features, we can reduce number of features, and all these steps could be combined in pipelines. A pipeline is a term which commonly used in scikit-learn and Spark ML Leap. Also in the next stage we have model training. We have cross-validation, which can be done with the R. Also cross-validation could be done in scikit-learn, and Spark ML Leap also allows us to do cross-validation. Also we have at this stage we should choose proper model, and evaluate this model, it's suitable for our task or not. And in the final step, we have final model, because after training we have pre-trained model, and we build it into pipeline for processing data, and we can use it for processing data which we want to something predict, classify, or clustering, and we can interpret this, make some interpretation of the results of using of this model. These are all part of our workflow. Also, if you're talking about Spark ML, because we are talking about this framework, Spark's machine learning module ships common machine learning algorithms. So, common machine learning algorithms. I'm talking about statistics, linear algebra. We are talking about tools for feature extraction. We are talking about things like decision tree. We are talking about regressors and etc. Also, we have tools to load, extract, transform, and select features. We have ability to chain multiple operations using pipeline, which I mentioned in a slide before. We have ability to save and load algorithms, models, and pipelines. We have capability of performing linear algebra and statistical operations. So all these. Initial release of Spark used the Spark ML Leap package that had RDD based APIs. With the Spark 2.0, a new package called spark.ml was introduced that operated upon data frame. Main idea of this sentence, that if you are using older Spark version, you will work with RDDs, resilient distributed data frame, and you will use Spark ML Leap. But if you are using newer version of a Spark, I'm talking about Spark 2.0, 2.4, 2.3, and we are talking about Spark 3.0, which we'll use in our class. We are talking about library spark.ml, and we will work with the data frames. So we shift from RDDs to data frame, and it allows us to have many advantages, such as all benefits of data optimization. We can apply all machine learning library capabilities and all operations on this distributed data structure, which are rather efficient. Various data sources that are accessible via data frame can now be directly used in ML Leap. I'm talking about RDBMS. I'm talking about another data sources. Feature extraction and transformation can utilize Spark SQL operations. Data frame-based APIs also provides uniformly both within ML Leap operations and across Spark modules, and in a very user-friendly manner. Machine learning in general is a programming paradigm where existing data helps in either generalizing the results as in classification algorithms or make some predictions. Main concepts. Machine learning in general is a programming paradigm where existing data helps in either generalizing the results as in classification algorithms or make some predictions. Machine learning, the science of how computers learn without being explicitly programmed. You see this phrase which was told by one of the pioneers of machine learning. Machine learning can be categorized into 4 categories. It's supervised learning, algorithms that learn from existing data sets and then utilize them to predict output values or labels for unlabeled data sets. Consider supervised learning. We are talking about regression, when we predict some values, and we are talking about classification, when we categorize some things. So supervised learning. Supervised learning when somebody learn our model or algorithm. When you have to provide training data set which has some answer questions, and you can imagine it as you have a child, and this child to learn him, when you teach this train this child, you at first you gave him this child you give him question and some answers, and after your child train or learn, you ask some questions without answers, and you want to hear some response or answer on this question, and that's why it's called supervised learning. Unsupervised learning when your model or algorithm don't have any answers. This is task of clusterization usually, and we are talking about so unsupervised learning is exploratory in nature, and machine learning is used to find patterns or correlations among the input data sets. So machine tries to get some information and try to make some conclusions based on information which exists in its storage. And examples of unsupervised learning are k-means clustering and principal component analysis, PCA. We also have semi-supervised learning. Semi-supervised learning when it involves a hybrid approach of both supervised and unsupervised learning. For instance, speech and image-based processing utilize this approach to solve their domain-specific problems. In this case, we train our model, but less than in supervised learning. That means that the person who usually called as assessor will not prepare all of the training data sets. You have to understand that supervised learning sometimes is more expensive than semi-supervised learning, but for mission critical systems usually we are using supervised learning. For instance, if you have heard about some medical systems which are based on artificial intelligence, on machine learning, on deep learning, usually use supervised learning because the cost of the error is too high. If you are talking about some simplest things which are not so critical, we are talking about semi-supervised learning. Also, we are talking about reinforced learning. Reinforced learning is used in artificial intelligence and its related fields. It allows machines and software agents to automatically determine the ideal behavior within a specific context in order to maximize its performance. So we also have reinforced learning, and you see that it also commonly used. But now for machine learning in a Spark, with the Spark you have to understand that we have supervised learning, unsupervised and semi-supervised learning. All these methods could be provided by Spark ML, especially it has k-means clustering method, it has principal component analysis method. Also main concepts. We have some terminology we have to know and understand. At first, what are these terms? At first, this is feature. For any observation, feature represents a set of traits that describes the entity equivalent quantitatively. For any observation, feature represents a set of traits that describes the entity quantitatively. That means that if you have, your task is to describe some car, its features are colors, car model, number of seats, and so on. Your features could be of different types. It could be colors, it could be names, it could be numbers, real numbers, integer numbers, it could be logical some numbers. But usually you have to understand that when we train our machine, we also will convert them into digital form. If we have colors, red, green, blue, we will create 3 classes, 1, 2, 3, and we encode first a color with a 1, second color with a 2, third color with a 3. If you are talking about Boolean values, true or false, we will talk about 0, 1, for example. Yes, car model also could be encoded. There are multiple ways of encoding, but now you have to understand that feature or features are some input data we are working with. We also have label. Label is dependent entity whose outcome is related to the values of a feature, such as in case of features of a car depending on the car model and the number of seats, and the label could be the maker of the car. So it's some dependent entity. Outcome. Also imagine that you have another example. You have some flat. Maybe you rent some flat, you rent some house. And you have characteristics. I have 4 rooms. The square of the house is 100 square meters. Our house has garage. We have 2 bathrooms. We have 1 living room. We have kitchen. Imagine, yes, and we have maybe 3 bedroom. And the outcome will be, or label will be the price of the rent, or you want to buy this house. This is label. So feature are parameters of this flat, and label is outcome. For another domains, we have another features. For language, natural language, our language will be encoded into numbers also, and represented as a number of sentences, encoded sentences, encoded words, etc. And label could be, for instance, could be some results of semantic analysis, etc. Also, you have to understand the Spark ML Lib data types could be RDD based, older versions, and data frame based. I talked about it before. What about data types? We have these data types which are depicted here. First, we will start from local vector. What we see here, all of these data types you see here are local data types. These data types are not distributed among different nodes of our cluster. We have local vector, which is stored on a single machine, having values as double and indices of each such values are stored as an integer starting with 0. It's a local vector. It's like array. It also can be can further be subclassified into dense double array, representing its values as represented here, and sparse, which could be written like here. And here what you see here, if you have zeros, these zeros will be omitted, and in your vector will be saved only the number of elements and positions where you have these numbers. For instance, in 0 position you have 2.0, in position 2 we omit position 1, yes, we have 5.0, in position 3 you have 3.0, like here, and all other values are zeros. These are sparse vectors. So dense vectors, sparse vectors, dense matrix, sparse vectors, matrix. What about distributed matrix? Let's move to also labeled point, because I forgot about labeled point. Let's talk about labeled point is a dense or sparse local vector having a label or a response value. Used in supervised learning, more prominently in classification and regression based algorithms. So if we have multi-class classification, we have 0, 1, 2, and etc. If we are talking about binary classification, we have 0 or 1. And if we are talking about regression, we have double values. Labeled point values are stored in a double data type. Regression usually used to predict something, some value. Also, we have local matrix. It's like two-dimensional array. It's stored on a single machine, and values are double data type. We have row and column indices in integer from 0 to n, from 0 to m. Can further be segregated into dense matrix and sparse matrix. What you see here. Values are stored in a single double array in column major order, and if you're talking about sparse matrix, it stores it in non-zero values in compressed sparse column, CSK format, in column major order. It's a bit specific format, but I think you will not have any problems if you try to understand. Okay, what about distributed matrix? It's stored in one or more RDDs, and hence it is distributed in nature. Row and column indices of distributed matrix are of type lon, while the values are of double type. So values in our distributed matrix are double, and indices are lon values. Conversion of distributed matrix to any other type may require shuffling, and that's why it's too expensive operation. Also, it could be classified into row matrix, inverted row matrix, coordinate matrix, and block matrix. Row matrix oriented distributed matrix without meaningful row indices, RDD of sequence of vector without row indices. So what you have? You have rows, but the order of these rows is not important. If you have index row matrix, then we take into account indices of our rows. If you're talking about coordinate matrix, you have element values, and they could be defined as depicted here. You have also block matrix, which allows you to work with the blocks of this matrix when you have some block or sub-block. What about machine learning workflow? We have training. When we load our data, we extract our features, we train our model, we evaluate it. That's why when we train. When we test it, we load our test data, we extract the features, we predict using model, and we obtain the result. So we have training the model. So iteration over the same set of training data over and over again, while only changing the tuning parameters to achieve minima in error while evaluating the values on training data, and only then the model is fed with the test data to give resultant output. testing the trained model with newer data sets. That's very important, that if you're talking about learning, what is the learning between learning and remembering? Because when you are training, when you learn something, you are what you are doing. You are you have questions, you have answers. Yes, but if you can't estimate the accuracy of your model, and you give to your machine or model some unpredictable results, values, features, you can obtain an unpredictable result. Testing and the trained model with newer data sets, that's training. Also, I omitted data preprocessing, feature extraction, model fitting, and validation stages here. What about pipelines and how we move to them? So in our case, data type will be data frame, and we also have operations which called transformers. Transformer transforms a data frame into another data frame by either adding a few more columns in the existing data set or changing the data frame values itself and thereby giving the resultant in a new data frame. In this case, the method named transform. We have binarizer transformer converts input columns of data frame into 0 or 1 depending on a threshold value. We have a machine learning model which accepts feature vector from data frame and then appends the predicted label as a new column to the resultant data frame. So binarizer transformer converts input columns of data frame into 0 or 1 depending on a threshold value. Machine learning model accepts feature vector from a data frame and then appends the predicted label as a new column to the resultant data frame. We also have estimator. Any machine learning algorithm that trains or feeds on the learning data to produce a model, which again is a transformer. The model then transforms the test data, producing resultant values in the output data frame. Has method fit, which invoked on learning data frame in order to generate a model that can transform the input data. Examples is the k-mean method or decision tree. We have estimators in both cases. In the first case, we produce k-means model. In the second case, we have decision tree model. And pipeline allows us to combine all these methods together. Sequence of job chaining is specific to an algorithm or use case and hence the order of pipeline stages. In our task, we will talk, we will talk about linear regression. It's a commonly used method for regression analysis. We have simplest case when we are talking about our equation in the form of line. But about regression we talked in our one of our previous classes. Today we will talk about example when we use the model of when we will use model of linear regression. We will try to predict the values of total impression, which is some total of like, comment and share that a Facebook post will get depending on the feature vector parameters such as post month, post weekday, post hour, and so on. I will show for you now this example. This is the example we'll talk about, but at first I will tell you what about also about operations on feature vectors and what we will do. We have feature extractors, we have feature transformers, and we have feature selectors. Feature extractors could be subdivided into count vectorizer, term frequency, inverse document frequency, term frequency, and inverse document frequency. All of these things allows us to get information about text data. And if we are talking about feature transformers, we are talking about tokenizers, stop words remover, vector assembler. And if you're talking feature selectors, we are talking about he-square selector, and we have vector slicer. All of these you can see here. Okay, let's move to our example. What we will do? We'll talk about our project. Just a moment, it hangs up. My project. We will create our small project to show for you how to create your own machine learning program with the Spark. Just a moment. All these things I will show you, but our task will be a linear regression. It will be our task, linear regression. At first, I will prepare this project in Java language. What I will do at first about dependencies of our project. Dependencies of our project are the next. We should add. It is a Java application. We are talking about shadow plugin. This plugin allows us to create something which called fat-jar. It's a key which contains all of our libraries needed to run this program, because only with this tool we can submit this task into cluster. And what about dependencies? Dependencies are very simple. It's Spark ML lib, Spark core, and Spark SQL. And also option of for shadow jar, it's zip64. This option tell that we should support large amount of files. Let's move to our code and let's comment this code. We take some data. Let me show for you this data. These data are Facebook metrics. These data are Facebook metrics. And what are these data? It is just a moment. It is data, and this data contains page total, likes, type, category, post month, post week, day, post hour, paid lifetime post total reach, lifetime post total impressions, and etc. And we have also here total interactions. You see total interactions. According to our task, we have what we have. We will have features and we will have target or label. So here, okay, let's move through our code. Usually it's a class, as a usual class. We declare some pass to our one. If you want to save our model, we will save it. And if you want to save our results, we can also save these results. What we'll do here, we have passed to our data. We also better, okay, in this case, yes, it's not good option. Better to extract this constant. It's our regression data set. Let it be in this way. So we have pass to our input data, we will have pass to our output data, and pass to our model, because when we train it, we want to save this model. At first, we are creating Spark configuration. We set the application name. We set that it should be executed in a local mode. We create Java Spark context based on this configuration. We create Spark session. We create SQL context to process data with the SQL framework. Here we describe our data structure. Our CSV file, which you see here, all of these fields, what we see here? We see here integer values, we see here string values, and also these are all integer values. And if you look here, what you will see that we have integer data type, string type, integer, integer, and all of these are integer data types. And here what you will see the name of the column in a CSV format. It's a page total likes type. It's a columnar. It's like table. CSV format, comma separated values. So you load this data. No, we not load. Now we only describe this data. We describe data structure. At this stage, we describe data set, and here we get only needed data. So you see that we to keep the model simple, we will select only few columns from preceding data set and call it formatted df. So we take only page total likes, category, post month, post weekend, post hour, paid lifetime people who have liked your page and engaged with your post, total interactions. We persist our data. We have take save column for some purposes. If you need, you can read that these purposes are available. We can print this input data on the screen. And now what we are doing, we split our data set into training and test data set. From the feature vector formatted def, we will split the data set into two. One trained data set and other is test data set. So we have 70% of our data will be training data, and 0.3 or 30% will be test data. On this data, our system is train, and with this data, it's testing. Also, our feature column are all except total interactions. So total interactions is our label or target or result. At first, we should, for linear regression, convert all of these columns and combine them together in one single vector. We are using for this class vector assembler. Also, we can scale them if needed. Scale sometimes is needed when we have a very large range of our values and we need to normalize them. And we pass our instance of vector assembler to pipeline, yes, and set the name that it's total interactions. Set feature column, row features. Set, we have max iteration is 10. Regression parameter is 0.3. Elastic net parameter is 0.8. All of these parameters are these two parameters are hyperparameters of our model. The next, we combine pipeline into pipeline. We combine vector assembler and linear regression. We combine them into pipeline. If we need, if you want, we can also scalar add here. We fit or train our model. This is the training process. Then we save our model, train model, into this file. And then if you want, we can load our model, and transform is using of this model. This is our program. And then we show prediction, the prediction. We can run our program. And you could see the result of execution. It's executed, yes, work. So what we see here, what we saw here, here is our input data, not the whole data set, but only columns we selected. We see that we split our data set into about 500. Size of our data set is 500 about, and we split into two: train data set and test. And then we can see this is our and also we have results which we have prediction. It's here, prediction. So the predictions are, you can see here, we have row features and we have predictions. So row features is a combination of all of these fields in one, and prediction is a result of our working of our model. So that's how look like execution of this program. This is main idea.